Okay, this section is about airplane flight controls, and we can control the attitude of the aircraft. Its different axes, which rotate around the center of gravity of the aircraft, through the deflection of our flight controls. Those flight controls either change the camber, their camber, or their angle of attack, which can result in more or less lift, thus causing us to rotate amongst the three different axes of the aircraft. We're going to talk about just a general overview, the chord line of a airfoil and its camber and how those relate to lift. We're going to cover the primary flight controls, which are our ailerons, our rudder, and our elevator, and then we're going to talk about our secondary flight control systems, which these improve our performance characteristics, and they can also relieve some excessive control force. Those would be our wing flaps and our trim system. So, and then we'll go from there. First two things that we're going to talk about are the chord line and the camber of an airfoil. And as we've discussed before, and as we know, an airfoil typically has a curved upper surface and a flat lower surface. And what that does is the airflow over top of the airfoil moves faster than the airflow on the bottom. And based on Bernoulli's principle, that's going to create a low pressure area at the top. We have a line that goes from the leading edge to the trailing edge, and that's called the chord line. So we need to gain an understanding of what angle of attack is. We have a relative wind that comes at our airfoil, and the relative or the angle of attack is where that relative wind is in reference to that chord line. So, for example, this would be a near 0 degree angle of attack, and if our relative wind was coming from down here, our relative wind also happens to be inverse to our flight path. If our relative wind comes down here, we're going to have an angle between this relative chord line, or between the relative wind and the chord line, and that's called our angle of attack also. So this would be something, maybe along the lines of 10 degrees. Higher angles of attack typically generate more lift. Next thing we want to talk about is the camber of the wing. The amount of curvature of the upper surface of the wing is going to determine how much lift that we generate. So in flight, our flight controls are used to modify this camber. Okay, in general, flight controls are hinged devices on the trailing edge of our airfoils. Our airfoils would include our horizontal stabilizer, our vertical stabilizer, and our wings. So what that does is that takes the normal camber, if we took our average camber line, and if we add to it, we're creating much more camber, more curvature, so that equals more lift. So that's the premise that all these different airfoils work on.
We're going to talk about ailerons and their effectiveness in controlling an aircraft and changing its flight path. An aileron is simply a control surface that's hinged to the trailing edge of a wing, and it's actuated by the pilot through the yoke and then through a series of cables and pulleys, levers and rods, or a hydraulic system. And what happens when the pilot, for instance, turns the yoke to the left aileron is raised into the relative wind, and the right aileron is lowered into the relative wind. What this does is changes the camber and the mean chord line of each of the airfoils. The way it works, we have an example, an airplane being banked to the left. The left aileron has been raised into the relative wind, and we can see a decrease in the camber and also a decrease in the angle of attack, as opposed to if the aileron was neutral. And on the aileron that's dropped into the relative wind, lowered into the relative wind. We can see how it has an increase in camber and also an increase in angle of attack, as opposed to if the flight control was just in its neutral position. So what this is going to cause on the aileron that's lowered into the wind on the right for a left-hand turn is an increase in lift, causing the wing to raise. The aileron raised into the relative wind with a lowered camber and a lowered angle of attack is going to cause a drop. And what this is going to do is going to change our component of lift on the aircraft. What does that mean? If we have an aircraft flying straight and level, its lift is generated vertically. If we have an aircraft in a bank, it now has another component of lift. It has a vertical component of lift and a horizontal component of lift. So in this scenario, the airplane is being banked. It's creating a horizontal component of lift, which is literally pulling the aircraft into a turn. And what that does is it creates a change in the relative wind. And the relative wind, instead of coming from straight on the nose, is coming at a slight angle. So if we were to look at our vertical stabilizer from a top-down view, this was our relative wind when flying straight. Now we bank the aircraft, we have a horizontal component of lift pulling us into a turn. Our relative wind is now coming from a slight angle. This wind is going to hit this side of our control surface, causing it to be pushed this way. And it's a simple fact of weather vaning. The aircraft tries to weather vane itself back into the relative wind. Now we do have some errors associated with the ailerons. When the lowered aileron, which is creating the lift, thus rowing the aircraft, when it produces that lift, it creates induced drag. Any increase in drag is going to cause a yawing moment about a wing. Let's see how we do it. We'll draw a top-down view. So this airplane's going left. This aileron has been dropped into the wind, creating more lift and more induced drag, which is going to cause a yawing moment back this way. But we're wanting our aircraft to go this way. So it's not going to cancel it out, but it's going to kind of cause the nose to go slightly in the opposite direction of our desired turn. So we can either counter this by adding a rudder force to try to push the aircraft back in the direction of our desired turn, or what some engineers have done on some devices has made what they call a differential aileron, where the aileron that is raised into the wind raises at a greater degree than the one dropped into the wind, instead of them acting the same symmetrically. So what this is going to do is create more drag on the raised aileron, thus causing a yawing moment this way, helping the aircraft go this way. Since we're pivoting about a CG, these two forces are working with each other. Another thing is called the freeze aileron. The freeze aileron, from looking at a cutaway view, is an aileron that's hinged offset. So when the aileron is deflected up, the leading edge of the aileron is dropped into the relative wind, causing drag, which would be on this aileron here, and thus also causing that yawing moment, helping the airplane to turn in the desired direction.
Okay, we'll talk about the elevator now. And the elevator is located along the horizontal stabilizer of the aircraft. And some key things to note about the elevator are it works along the same principle as far as the ailerons do. It's connected by a metal rods and mechanical linkage. It can be actuated by hydraulics. Those can even be fly-by-wire systems in which, when we deflect controls inside the aircraft, it sends electrical signals to servos that are located back there, and those servos engage the aileron in whatever direction that they need to go in. So that was one of the main points about that. And the principle that we're working with is the horizontal stabilizer of the aircraft is also an airfoil. And that airfoil has a camber, and it has a curvature on the upper surface and a flat side on the lower surface. So that generates lift as well. However, what we're doing is we're actually pivoting the aircraft the longitudinal axis about the lateral axis of the aircraft. So what the elevator does is if we push forward or if we pull back on the yoke, the elevator is going to go up. We've got a drawing of an aircraft here. If we push forward or pull back on the yoke, the elevator goes up. And what that does is it reduces our camber, it reduces our lift, and what will happen is the tail of the aircraft will go down and the nose of the aircraft will go up because we're rotating about the center of gravity of the aircraft. Conversely, if we push the yoke down, and which means we will push the elevator down also, that will create an increased camber, increased angle of attack, which will thus create lift, and that lift will rotate the lateral axis or the longitudinal axis about the lateral axis and make the nose of the aircraft go down. Alright, how effective is the elevator is another thing that we need to cover. Well, the distance that we have from this center of gravity to that elevator is an arm, which is something that we'll probably talk about later in weight and balance. But that arm creates a moment. It creates a force. The further the distance is, the stronger that force is. So the any kind of control inputs or whatnot that we have, again, that further distance, they'll be more effective, and that will be more of a force that's created by that arm. There'll be more of a moment, so to speak. So the different types of tails that we have. We've got a conventional tail as illustrated right here, and this conventional tail it has a good advantage in that it takes any kind of airflow. Say we have a propeller, it takes any kind of induced airflow and takes that into account because with our lift equation, we'll take note that velocity has a lot to do with how much lift is generated. It's right there in the lift equation. So the more velocity that we have, the more lift, the more effective that the control surface is going to be, because these do depend on air flowing over them, as we've talked about with lift in general. So if we were to maintain a constant power setting, that would be great. However, a lot of times we're at different power settings, so the reliability of control input does have a lot to do with how much induced airflow from either our propeller engines or our jet engines are flowing over that. Now, on the other hand, we have a T-tail, and a T-tail gets rid of the induced airflow from the propeller or any kind of jet wash that comes out. And what that does is it gives us a little more reliability in control as to what we can expect through a wide range of different airspeeds, because we don't have that induced airflow. The one thing that is a challenge with that is at low airspeeds, without that induced airflow, it's going to require more control input on our part to get the same desired results, since we've taken that out of the induced airflow area. So next, we can talk about a stabilator. And what a stabilator does is the entire horizontal stabilizer pivots. So it could be like that, it could be like that, or it could be like that. Now, that's going to make a huge, huge difference in the amount of control input required, because that's going to create a very, very large moment. Some of the things with that to keep in mind is if we pull back on the yoke, what that's going to do is that's going to take the trailing edge if we pull back, the trailing edge is going to raise, much like this. That's creating a negative angle of attack that pulls the tail of the aircraft down, which rotates the nose up, and vice versa if we push the nose down. Stabilator is going to go like that. It's going to create a high angle of attack. That high angle of attack is going to generate lift, thus rotating the longitudinal axis about the lateral axis of the aircraft. Some things that we have to keep in mind with this are there are anti-servo tabs on these to keep us from making too much movement. They'll move in the same direction to kind of counteract some of that, and so that's about it.
Right now we're going to talk about the rudder, which is an airfoil. It's a flight control surface that's activated by the pilot through the rudder pedals, which are linked by cables, push rods, servos, or hydraulic pressure. And this is actually a symmetrical airfoil as opposed to the wings, which are an asymmetric airfoil, which are designed to create lift in one direction. The rudder can create lift in either direction, as well as the elevators do the same thing. Our rudder is simply an airfoil, vertical stabilizer, with the rudder as a control surface at the back of the vertical stabilizer. And what happens is the aircraft, there's our fuselage of the aircraft and wings on up ahead, the relative wind in straight flight is hitting this rudder equally in all directions from the front.
Vertical
and obviously,
stabilizer.
The what?
Vertical stabilizer.
Whatever the fuck it's called, I don't give a shit. It looks like this. Looks like a big fucking pecker with some grass growing out the tip. Alright? Alright, now we're going to talk about the rudder and vertical stabilizer. The rudder and vertical stabilizer are coupled together in an airfoil, and it's activated by the pilot through the rudder pedals and a series of cables and pulleys or push rods or hydraulic. And what it is a symmetrical airfoil as opposed to the wings, which are an asymmetric airfoil. And asymmetric airfoil is designed to produce lift in one direction, where a symmetrical airfoil can produce lift in either direction. And what we have is our vertical stabilizer, and the control surface at the trailing edge is our rudder. And this is symmetrical. Here's our relative wind flowing over the vertical stabilizer and rudder, thus causing it to weather vane into the wind. Now what happens when we put, let's say in this example, push the right rudder pedal? The rudder itself deflects to the right. Now a relative wind flowing over this is actually going to contact the rudder, causing a yawing moment, a pivot about the vertical axis at the center of gravity, yawing the airplane, in this case, to the right. And the opposite when we press the left rudder pedal. It's as simple as that. Now there are some problems associated with this. We call it proverse roll. And it's a fairly simple concept. If we have an aircraft and we have deflected our rudder to the right, we're desiring the aircraft just to yaw to the right. We've not given any kind of an aileron input at all, just rudder. So what happens is, when this aircraft is turning, we can make a very simple example. We have an aircraft right here, pivoting about this point. The wing towards the inside of that turn has got this much distance to travel to complete that turn. The outside wing has to travel this amount of distance in the same amount of time to complete that turn. So what's happening? You're having a greater flow of air over the outside wing as opposed to the inside wing. So in this situation where the aircraft is being yawed to the right, this wing here is creating more lift simply because it's traveling through the relative air faster, the relative wind, and it's going to cause the aircraft to roll to the direction of the turn that we've input through the rudder.
Okay, you forgot one thing.
Okay, we're going to talk about trim tabs. And what is a trim tab? A trim tab is a secondary flight control. It is located in this situation we'll be talking about the elevator trim tab. It's located on the trailing edge of the elevator. We have what we call an anti-servo tab and a balance tab. We also have ground adjustable trim tabs. And what their purpose is to alleviate some of the control pressures a pilot has to input on the flight controls to maintain, in this situation, a straight and level flight as far as the nose's pitching attitudes are concerned. And what happens is, depending on how the aircraft is loaded and different characteristics of the aircraft, it will tend to either have a pitch up or a pitch down attitude in straight and level flight, and can cause pilot fatigue and an extra workload on the pilot to maintain that level attitude. And so trim tabs of different types have been devised to be able to limit the pilot's workload and make it a hands-off flying situation for the pilot. We're going to talk about the balanced trim tab first. A balanced trim tab is a trim tab we have on our Cessnas, and when the elevator is deflected, the trim tab moves in the opposite direction of the elevator. And to explain how this works, we're going to use a straight and level flight scenario to try to get our head around this. When an aircraft is in straight and level flight, the CG is forward of the center of pressure. So what this means is we always have a nose down force, which is going to create a seemingly tail up force, simply because we can imagine this pivots about the center of gravity. So what we have to do is have the elevator and horizontal stabilizer mounted to the aircraft. Its angle of incidence it's already predetermined by the manufacturer with a tail down force to compensate for that. And this force can be seen acted as a nose up force. So if our weight of gravity forward of the CG, the nose down force, let's call it force A, is seen as a tail up force of equivalent force, and the tail down force, to cancel out the nose down force, we'll call this B, is seen as a pivot in the nose of the aircraft. So A forces and B forces are canceling each other out. We'll say in this situation we have too much weight in the rear. We have a tail down, nose up situation. So that means our force B is greater than A. So as we can see, we have a greater nose up force and we do nose down, so this is going to obviously cause us to climb. So the pilot activates the trim tab by a control wheel, usually located in the console or between the pilot and co-pilot seats. It's a vertical wheel. It's rotated forward for nose down trim, backwards for nose up trim, and is usually attached to the trim tab via a series of cables. And so what happens if we trim for a nose down? We roll the trim tab wheel forward, which is actually going to cause, in this situation, the trim tab to go up. And that's, like we said, is located on the trailing edge of the elevator. What this is doing is actually projecting itself into the relative wind, which is causing this flight control, the elevator, to be deflected downwards. What this is doing is it's decreasing our angle of attack. It's decreasing the amount of tail down force that we have in the aircraft. So it's taking this tail down force and it's decreasing it. And so what does that mean about our nose up attitude? Like we said, the tail down force is noticed right here. So now we've decreased our tail down force and we've decreased the nose up force. So now forces A and B are acting in the same amount. And an anti-servo tab is located on a stabilator, which we've already discussed earlier. And a stabilator, when moved, the entire control surface moves because it hinges about a point which we can compare to a center of gravity. And that's how we can picture its movement. And the anti-servo tab actually moves in the same direction as the stabilator itself. But in this situation, like we said, we're imitating straight and level flight with a nose up attitude. And the opposite is true for a nose down attitude. We just pick nose up. So this means that our tail down force is too great, causing our nose to rise. So what do? Same scenario. Take the trim wheel, spin it forward through the linkages. It brings up the anti-servo tab, which again brings this into the relative wind, causing the surface to be deflected downward. So the surface deflected more downward, again it decreases the angle of attack and decreases the lift that the stabilator is producing in the downward motion, of course. So that tail down force is lessened, and the indication the pilot gets, which would have been the nose up, is also lessened. So now our force A and force B are equaling each other. And the ground adjustable trim tabs, actually simpler in mechanism, yet probably a little more difficult to fine tune. They're simply a metal tab that's fixed to the trailing edge of your flight control surfaces, be it the elevators, the rudder, the ailerons. And you actually adjust those on the ground, and they have the same operational characteristics as the ones that are changeable by the pilot. They are one-time use kind of things. You try it, you go up and fly. That either was or wasn't enough. Come back and do it again. So they're not very accurate. They're not adjustable during flight, and that's about all we have for our trim tabs.
Okay, we're going to talk about flaps and some of their advantages, what they're for. And a flap is a high lift device that's located on the trailing edge of our wings, and the purpose of the flap is to create additional lift and induce drag. And the reason that we use flaps is it permits us to fly our approaches at lower speeds, at higher angles of attack, and it also allows us to make our approaches more steep without increasing speed, which is critical in things like obstacle avoidance. We have several different kinds of flaps. The first one that I want to cover is a plain flap, which is pretty easy to understand. It's just a hinge device on the back of our wing, and it would look something like this. That would be our flap right there. This is called a plain flap, and it's going to increase the camber of the wing, and it's also going to really increase our induced drag, and that's a plain flap. And that's really the simplest type of flap. From there, we have some aircraft that have been equipped with what's called a split flap, and that's where the flap tends to drop like that from under the surface of the wing. And with a split flap, we do get a little bit more lift than we would get from a plain flap. However, we get much more induced drag because of the turbulent airflow that's created behind the flap. Now, most of the aircraft that we deal with today, a lot of aircraft have been equipped with what's called a slotted flap. And what a slotted flap does is a slotted flap allows airflow that normally wouldn't exist with our plain or our split flap. And the good thing about this airflow is that the airflow that comes under the wing is allowed to join the airflow from the upper surface of the wing, and it's high velocity airflow, and it delays the separation of the airflow from the boundary layer. resulting in more lift. So there's not an early separation when they join together. That high velocity air keeps that airflow over this increased cambered surface for a longer period of time. So that's one of the significant advantages to this type of flap, the slotted flap. The other flap that I want to cover is what's called our Fowler flap. And our Fowler flap is slotted like a slotted flap, but it also works by increasing the surface area of our wing. So we're going to get the most lift out of a Fowler type flap. The flap is kind of on tracks. So what happens is, and I'm going to redraw this so I get a little more room here. Okay. The flap is on a track. So rather than just being a normal slotted flap like this flap has a track that extends the surface area out here. Okay, on that track. Like that. So what that does is increase the surface area. It gives us the most amount of available lift. And we still have the high velocity airflow from under the wing that meets and delays the separation from the boundary layer. So how can a pilot use the flaps? Pilot can actuate the flaps. They're usually either driven by some kind of motor, whether that be mechanical or they could be hydraulically actuated. In some craft, they're still even mechanically actuated, but those are typically how we can deploy those flaps. And the advantages of that are it gives us better slow speed characteristics. Some aircraft, their wings are obviously designed for high speed flight, and so to be able to safely land the aircraft, they need to be able to come in at lower speeds, and that's typically what our flaps are going to help us for. Flaps in some cases can be even used during takeoff to increase lift and whatnot. So that's pretty much what I wanted to cover on flaps.